Okay, so on Monday, after we went over the material, it was quite a lot, I admit. On Monday, we had, if you recall, we had 6 boxes or 6 menu items that we needed to get through. The first day, we went through the first 3, and for last Monday, I went over the first 3 again, and then we added on 2 of them. We have not yet gotten to the last one, the 6th box, but we did 2 more, which was conditional probability and Bayesian theorem or Bayes theory, which is built on top of the conditional probability. And we had some exercises to familiarize you guys with the problems that could come up with the first 5 boxes, so to speak, and we will go over them today. Okay, so this is nothing new, hopefully. This is set theory, and I already took a peek at some of you guys' answers on Scale, and I think you guys have it down, but just in case, we'll go over them once more. And I need to move over my keyboard and get my tablet here, so give me a second. Okay, so you can solve this 2 ways. You can use logic, and I saw that some of you have explained your answers here, but you can also draw the Venn diagram just to get the idea a little bit clearer. So I'm going to draw a Venn diagram. Oops, it's not straight, but you get my idea. This is my universe. I have a set E, for example, and I want to denote E first, just to make ourselves clear. This is E. Everything in this circle is E. And I also need to know, oops, no, can I change the color? Oh, here. I also want to know E complement. So remember, E complement is everything except E. Ooh, everything except E. There you go. So if I were to join the 2 together, the annotation here that I'm using is union. So I want to join together E and everything that is not E, I get my universe, or in the context of probability, this would be my sample space. So hopefully you all got this. This equals to sample space. Okay, next, we are also once again looking at E, the same thing from the same Venn diagram that I drew on top. And then we're also looking at E complement over here. Okay, and instead of the union, so the first one we were joining together, we're taking the intersection. So since we know that E is E, E complement is everything other than E, then their complement, their intersection would be, anyone? You can use the chat box. Help me out here.
Is it an empty set, miss?
Exactly. It should be an empty set, which you can denote either like that, or you can also denote it using that symbol. So both of these are empty sets. Okay. So on your exercise, I only gave you the first 2 questions, A and B. However, here in the exercise together today, I added on 1 more. So this is a challenge question, so to speak. You need to use some of the rules that you learned in math and discrete math that we went over very quickly. I just showed you a slide on the distributive law, commutative law, and so on. But to help us visualize this problem, I will once again draw a Venn diagram just to make things clear. This is our sample space. And this time I have 2 sets of E. There you go. And I also have another set of F. I'm just going to draw them with an intersection just in case. We don't know yet if their intersection exists or not. So the first part of the equation here, I'll use a different color. I'll use orange just to make things clear. It is E union F, E and F. So it's both E and F. So it would be this area here, the two balls, the two circles. Now the next one is a little bit trickier. So we have E union F complement. So let's work on the F complement first. So F complement would be everything other than F, correct? Oh, except F, something like that, outside of F. And I want to make a union with E. So E would be this here, regardless of F. So this little intersection, which is part of F, which was not included in F complement, however, it is then included in E, in the E part, this part. Okay, so I have my purple shade here, and I have my orange shade in the middle. Let's redo the orange one just to make it clear. My orange. And I need to intersect the two of them. Does anyone have an idea or an inkling what the intersection would be? Or in other words, what's the intersection of my orange and purple shading here? Anyone? Take your time. Oops, there is a chat already. Okay, Atar says E. I think that's correct. Thank you, Atar. So the purple ones is everything except F. The orange one was everything except F plus E, and the orange part is E and F. So exactly, this would be the intersection between the two. So you can do it like that using the Venn diagram to help you out, which is completely fine. However, we can also restructure this equation as follows. So E union F would be the same as F union E. And the right-hand part, E union F complement would also be F complement union E. So if you recall, I think it's a distribution rule or something, not so quite sure, but this would be equal to F union, intersection F complement union E. Should be something like this. And recall F intersection F complement, or just what we just solved in B, this would be an empty set. Or you can also use this symbol. It would be an empty set. An empty set, we join it with E, obviously would be equal to E, which brings us back to the E that we had previously. I believe, yes, this was my writing that I did for last year's class. It's still valid, the same for the same way that we just did. And I'm going to take a pause here. Any questions? Since we were talking about sets, I thought to review some of the sets. So for number one, this is just a little tricky. However, it is a multiple choice question, so hopefully that helps you out in selecting the answer. So in case you're interested, I believe B is the answer. I believe so. I believe B is the answer. I should check, but I believe B is the answer, but let's go check. A union B, oops. A union B complement. So A would be this one. Would be A. B complement would be everything aside from B. I'll go the other way just to distinguish the two. Everything outside of B, that's the first part, A union B. And I would need to intersect it. No, give me the colors. Please intersect it with C. So I only need to, I would like to intersect it with C. Yeah, there we go. That's C. And that would bring us to our final answer of, I have to change the color again. Come on. Come on, give it. Oh, well, let's just make it green. It would be this area here. Okay, so that's the first one. And the second one, it has to do, I think it's on your exercise, the second question here. So if E and F are two mutually exclusive events, is this expression always correct? This one here equals S. So let's talk about what we do know. Let's try to see what we do know about these two things. Seriously, hello, give me, okay. So I have a union, a sample space. I have E and I have F. E and F. If E and F are mutually exclusive, so I know that they are not intersecting each other. Is it correct that E union F will equal S? So in other words, if I have E there and I have F there, would E joined with F be encompass all of the members of S? Obviously, it depends. Are there any elements of S outside of here or not, right? So the mutual exclusivity does not ensure that the sum will be equal to the entire sample space. Not only do we need to ensure that they are mutually exclusive, but we also need to know if they are complete exhaustive. I think that the term is completely exhaustive. I think this is the correct term. So let's collaboratively exhaustive or completely. I remember it's CE. Let's open my cheat sheet for a second. Collectively exhaustive. Okay, so not that far off. They have to be collectively, not completely. Collectively exhaustive. So the answer is only if E and F are collectively exhaustive, this expression would be correct. Okay, so this is the next question about probability. I think I'm going to just move on because I have something interesting to share after this question. So before we even try to do this, I want to draw your attention to the fact that we can solve this question in two ways. There are two ways we can look at this question, and both of them are valid. I noticed that myself, when I was solving this and making a key for this exercise, I did it in method A. However, a lot of you, I already looked at your submissions, did it the other way, but both is valid. Let's look at the way I tried to solve this first. So first of all, don't forget that you always have to declare what your letters mean, right? So I'm going to use the letter W, my brother waters my plant. Okay, and I'm going to use D as my plant dies. Plant dies. So using these two letters, we can now write down what information we know. So we have, what's the probability that my brother will actually water my plant? I'm 90% certain. So the probability would be 0.9. So let's look at these two numbers here. Without water, my plant will die with a probability of 0.8. So my plant will die given that it is not watered with a probability of 0.8, and the probability that it will die with water is 0.8. Short pause here. Anyone confused up until here? Please feel free to say so, no problem. I'll take a short pause, drink break. Okay, please feel free to stop me at any time, but I'll continue. Okay, so I could look at this a couple ways. The first way is I could try to compute the probability that my plant dies. How can I compute the plant dying? Well, I would need to consider it dying and my brother watered it, and the plant dying and my brother did not water it. And we already learned this, that if we only have two, then we only need to sum them up. But if we have more than two possibilities of conditions, then we need to sum up more. But in this case, I only have two. It gets water or it does not get water. And if you remember, we have a conditional probability equation, which I will write in the corner here, just so that we never, ever, ever forget it. If I want to compute P intersection, so D intersection W, or in this case, in the equation, it's written EF, I can compute this by multiplying PE given F times PF, right? That's math, that's basic math. Hopefully I don't need to explain to you why. Oops, wrong color. Come on. So we can then compute the probability of my plant dying given that it is watered times the probability that it is watered plus the probability that it dies given it was not watered with the probability of it not getting watered. So first of all, we know the probability of getting watered. As such, we can also know that the probability of it not getting watered would be 1 minus 0.9 or 0.1. So in this case, we can compute 0.15 times 0.9 times 0.8 times 0.1. So from my calculations, this will end up to 0.215, I believe. Give me a second. I did this computation on my cell phone calculator just a bit. Okay, yes. 0.215. Please correct me if I am wrong. And since this is the probability that my plant will die, then the probability that my plant will not die or be alive would thus be 0.1 minus 0.215 equals 0.785. And that is our final answer. Any questions up until here? This is solution. Method A. This is, I'm going to go over solution B again. Anyone? Okay, so the second part, I noticed a bunch of you did it this way. It is not incorrect. It is fine. It's correct. It's just a different way of doing. So you guys did another step of translating the information that we knew. So I have these questions, these answers here, right? These information here. So this is the probability that my plant dies given that my brother did not water it. You guys translated a little bit further. The probability that my plant is alive given that it is not watered, it will be 0.2. And the probability that my plant is alive given it was watered, it's 0.85. So I'm going to take a note right here on what you guys did in this section here. So what you did is PE complement F equals 1 minus PE given F. So I'm going to write that down here in green, just so we remember it, because we're going to talk about this property in a sec. Okay, so now if I know this information, now I can directly compute the probability of my plant not dying. Or in other words, I can now compute PEW plus PBCW like that. And that will bring us to the information that we already, W times PWC. And if I recall, this equation, this computation also ends up to 0.785. Okay, so there are two ways that you could look at this. So first, I can consider the opposite event, that what is asked, that I compute the complete probability, the total probability, and then I take the complement. And in this case, I do the opposite first. So I complement the probabilities I do know first, and then I directly compute the event that is asked. So as I mentioned, we're going to look at that green part over there. So we were under the assumption that this is valid, that PE complement F would be equal to 1 minus PE given F. So the first events, not the conditioning events, remember that the second one, at the given property, remember that the given property is the second one, the F. This is the conditioning event. But this event, if we consider the complements of each other, they will be 1 minus. So my question is, okay, we have proven that in our previous example that this is correct. The PE complement given F is indeed equal to 1 minus PE given F. The complements here is on the first term, E. So my question is, if we know that this first section, this first property is indeed true, we proved that in our previous example. What about this second one? I'm going to use a different color to distinguish them. If the PowerPoint will give it to me. Okay. What about that one? Okay, so I'm going to give you this food for thought. So, as a lot of you already answered in the chat box, the first statement is correct. The second one is not. Remember, when we were computing probabilities, we needed to make a fraction, right? We needed to put something as a numerator and one as the denominator. On top, we needed to put the number of elements in our event. And on the bottom, we needed to put the number of elements of our sample space. The first statement, the red statement here, it is using the same sample space, right? So the sample space is indeed F, or the conditioning event is F. That's our sample space. Our sample space is F. And over that sample space, we consider a complementary event, E and E complement. So yes, the complementary axiom of 1 minus is valid for the first statement, the red statement. However, on the right-hand side, this statement is the two different probabilities valid for two different sample spaces. The first one, on the left side of the equals sign, this is the conditioning event is F complement, and on the right-hand side, the conditioning event is F. So obviously, no, we cannot use the same rules that we did for the right-hand side. So I believe I have already written down. So I'm taking this from the source. So this is not the same. The complement formula only holds with respect to your first argument, or in this side, or on this, in the case of our equation here, E here, the first argument, the first event. So it is valid only for that, but not valid for the second one. The second one, you might ask, so then what's the valid equality for complements on the condition event? It doesn't exist. There is no corresponding formula for PAB complement. It does not work the same way. I believe that I also have, oh yeah, I do have a proof. So if you want to use the equations and you want to put it down, it can be valid for the first one, but not for the second one. If you wanted to derive the property from it, then you know that, like the right-hand side, the green writing here on the right. So we know that E complement given F is a complement towards event EF, but it's not valid for the condition. Okay, so hopefully that's clear. Please don't get mixed up when you are translating your the story or the question into your symbols, because it may affect your computation. Okay, so this is the last question on your exercise. So I remember before leaving class on Monday, Nicole asked me a question on how to interpret this question. So fair enough, I do believe that especially when you're writing in English, there can be some different interpretations here. So I'm going to explain to you what I meant by this question, and hopefully you guys got it, because I saw some of your submissions and I think you guys have got it right. So, you know, these days there's a bunch of influencers. You can be an influencer on practically any platform. You can do it on TikTok, you can do it on Instagram, whatever. But what does famous mean? Nothing to do with StatPro. I'm just trying to be relevant to the kids. So let's put together the information that we do know. So let's say that F is the, did I use F? I don't remember. So let's use F as the event in which a influencer is famous. And let's use C as the state as claims to be famous. Hey, I can also claim to be famous. I have more than 10 followers. So we're going to distinguish these two things. So let's put together these numbers that we know. So the first one, instead of what I wrote previously, this number here is the probability that the influencer says they're famous, given that they are indeed famous, 0.9. However, there's a probability of 0.5 that they will claim to be famous, even if they are not famous. Okay, so when they say they are famous, they are not actually famous. It is estimated that a total of 0.5% of influences can actually be categorized as famous. So the probability of someone actually being famous is, okay, this is 0.5%. So that's like 0.005, I believe. Suppose you ask a certain influencer if they are famous, calculate the following probability. So the first one is that compute the probability that the influencer will actually claim or say that they are famous. And P, this is the opposite. Remember from Bayesian theorem, this is the opposite. Given they claim to be famous, given they say famous, they are indeed actually famous. So I already computed that. So let's see. So this is the two things that I wrote on top just now. And this is the probability of someone actually being famous and the probability of them actually not being famous. And if I want to compute the influencer that will claim to be famous, PS, I need to consider both cases. This is the A here is exactly the same with what we computed with the plant, the previous exercise about the plant. So here we just need to sum up the cases in which they say they're famous and are indeed famous, and the opposite. And then we can compute, and then we get this number here. And the second one is the one that's a little bit more complex. So the probability of an influencer being actually famous, given that they claim or say that they're famous. So remember, this is from the conditional probability that we had right in front, P, E, F. I'm going to repeat this until you guys will no way forget it. That's our conditional probability here. So I use the same equation here. I use PFS over PS. And since PFS, probability of FS, is the same as PSF, it's the same thing. I can switch around the symbols. They're both intersection. Then this will also be equal to the multiplication of SF multiplied by F. These two things we know, the prior probabilities and the likelihoods, we already know that. So I can compute that. PS, I already computed it in A, so I can use that number again there, compute the probabilities, and I get a final number, more or less like this. I believe I used some rounding up here. So I rounded up some numbers. So you might get a couple of digits off at the end, but that's fine. In exercises